Okay, let's get started. So, hi everyone. Welcome to today's session. So last week we complete the introduction to bosonic codes, and so far we have a big picture of different kinds of error correction code for different error models. But however, we still don't know for like many of them how exactly we can fix the errors. So in the next two sessions, Tobias will guide us on decoders to find the right recovery operations when our system is hit by noise. So we will see how it works for classical and quantum codes, uh, deal with some real world imperfection like faulty measurements, so etc. And also like to obtain the error threshold. So let me hand over to Tobias. Yeah, thank you, Tobias.
Yeah, thank you, Sin, for the very nice introduction. So yeah, as mentioned, so I will talk about how to decode quantum error codes. So I think we've already heard many things about how quantum error works, how you construct codes. Right? We all had all different code types like surface code and subsystem codes and blockade codes and so forth, right? And so this is more now one of the practical or important aspects. How do we actually, once you have a code, how do you actually make use of it? Like how do you actually run it in practice, and then how do you actually get rid of the noise, right, in practice? How does it work? And this is a two part, so let's start with part one, this session. So I think I don't need to explain why quantum error is important, but just to recap. In quantum error, basically the main goal is we want to try somehow protect quantum information, which we call logic information, or we can also call that logic qubit. And let's say how we do this is basically we have, let's say, some qubit that we want to protect, right? This is some kind of quantum state in there that you want to basically keep away from the noise, right? Because there's always noise chipping in us, trying to attack us, right? This is just how the world works. There's like noise in the environment, and it just tries to kind of mess with us. And if you want to deal with this, the best way forward is to take our logic qubit and put it into many physics qubits in that quantum error code. So we encode one logic qubit into many physics qubits, right? So after that, basically, we have some kind of redundancy, right? Because we have now many physics qubits. Let's say the surface code, which we learned about, consists of, let's say, many physics qubits. And the logical information now somehow sits inside this huge number of physics qubits, right? But it's not really sitting on one physics qubit, but it's kind of delocalized, right? So somehow you can think of the logical information as somehow everywhere at the same time. It's in a weird entangled superposition of living in there. And this gives us some protection because we now have redundancy. And you can show, let's say we have our surface code, right? And let's say we have a surface code with distance d. You can show that, let's say we chuck out d-1 physics qubits, right? So we have distance d surface code, and let's say we somehow lose d-1 qubits, right? So this is supposed to be this black bar, this red bar here. So we just take d-1 qubits and just chuck them out, like they're gone, they're forever lost. You never see them again, right? If you can just think being these d-1 qubits, they're just thrown out, right? You just throw them out of your lab and you never talk to them again. Now, of course, you can think, of course, now we lost many qubits, right? That's bad. Now, but it turns out, if we use a quantum error code, the distance means that basically, although we lost d-1 physics qubits and we never talk to them again, and they're now part of the environment, the logical information, logic qubit is still okay, because we have this redundancy, right? And there's sufficient information to restore the original logic qubit by just looking at the remaining n d-1 qubits. So just by taking the rest number of qubits, you can still actually get the logical information back without any damage, in principle. Okay, so this is possible in practice, in principle, in theory. So the logical information, what I'm trying to say is logical information is still there. Okay, but in practice, something has happened, right? We lost, let's say, a bunch of qubits, right? Or some noise attacked us, right? So that means our code is now different than before, right? Let's say if we, as I mentioned before, let's say we lost these d-1 qubits. These qubits are gone, right? So meaning the code is not the same anymore. So we need somehow to restore the quantum error code to its original form, right? Somehow we need to kind of get rid of the noise or that affected. Basically, we need to restore the code state into its original form. And this can be done. This is done using what we call a correction operation. And for general noise, you can show that this is possible as long you have only d-1 half errors, right? So it's a bit lower than what we actually can do, right? While we know even with d-1 physical qubits, logic information is still there. If you actually want to do the correction, it turns out only d-1/2 is what we can actually correct against. Okay, and this step of basically kind of after being affected by noise, returning the code into its original form and applying a correction operator that kind of fixes the logic information, like puts in the correct form, this is called decoding. So this is basically the essential steps. Let's see how it works. This is shown this neat diagram here. You have some initial state rho. You have some kind of encoding, basically putting into a conversion code. How to do this we learned in the previous sessions. Then there is some noise. And finally, there is the decoding step. This is the green part here. Basically, after affected noise, you kind of restore everything into its original form and try to protect the information, the logic information. So the green part here, this is what we're going to talk about today. Okay, so clear so far? And oh yeah, I forgot to say, just if there's any questions or any comments or something like here, just interrupt me. So the key part is the first part of my talk is the most important one, right? So I talk about the most important parts first and then come less important things. So I want you to basically understand the most important parts as good as possible, right? So that's the key part, that you understand what's going on here. Okay, so let's start. And to explain, I will start with pretty much the simplest code you can think of, namely the 3-qubit repetition code. I think we may have seen this before in one of the earlier sessions. We've seen this code before, but just to recap, the 3-qubit repetition code is a code that protects against, in this case, X errors. The code states basically have some kind of logic qubit. The logical 0 state is just 3 zeros, and the logical 1 is 3 ones. And basically the logic information will be then basically just stored in the span, basically in a linear combination of the 0 logical and the 1 logical. Okay, and this is a code basically only protects against X errors, not against Z errors, because yeah, it's kind of missing some parts, but that's fine. You can see the 313 codes where the 3 distance only protects against X errors. Okay, so the final code, we also need our stabilizers, right? So basically we need to have the stabilizers that kind of check for errors. And for this code, the stabilizers are simply parity checks. So the first stabilizer is basically just checking the Z parity of the first 2 qubits. And the second stabilizer is checking the parity of the last 2 qubits. Okay. And you can write this in this conveniently form of a parity check matrix. This matrix is called the parity check matrix. So this is a matrix that basically where the rows are the number of stabilizers. So in this case, we have 2 stabilizers. So the row number is the row number is 2, and the number of columns is the number of possible errors, which in this case is just the number of qubits. And basically, the first stabilizer will be written as 110, right? Because basically we act only on the first 2 qubits, and 0 means we do nothing. And the second stabilizer will be written as 011 because we only act on the last 2 qubits. Therefore, we put ones there, and when we do nothing, where there's empty, we just put a 0. Okay. Now let's just play basic examples. We just assume that some error has happened. In particular, we assume an X error, an X flip has appeared on the first qubit. So if we have a logic qubit, for simplicity, let's say we initialized our error correction code in the 0 logical state, but it can be any state, doesn't matter. Any logical state is fine, but for simplicity, just assume it in a 0 logical state. Now, let's say some errors happened. There was some noise effect or some environment or some bad guy come and basically try to affect our qubits. But in the end, what happened is basically an X error happened on the first qubit. So the resulting state is now the 100 state, right? Which is not part of our code space. It's not a code word. So we know somehow in the error space. Okay, and we can now characterize this error by just an error vector. So the error vector basically is just a vector that basically indicates where an error has happened. In particular, we can write it as 100, right? Because we have an error on the first qubit and no errors on the second and third qubits. Okay, so this is the error vector. This thing characterizes the error that's happened. Now, this is the key part. How do you know this error vector? And in fact, this is non-trivial because in quantum error correction, we do not know the error vector. I mean, you could ask, okay, let's just measure for the error, right? Just let's say measure the first qubits and check whether it's a 0 and 1 state. Right? You could do that. But this is not allowed in quantum error correction because let's say if you try to actually directly measure the error vector and let's say start measuring, let's say the first qubit and ask the first qubit, are you in the 0 or 1 state? You will actually destroy the logic information because measurement on the first qubit would actually kill your logic information. Like this is an operation that is not allowed because it doesn't commute with the logical operation, with the logical state. So we cannot measure the error vector directly. It will destroy what we actually want to protect. So this is the kind of crux in quantum error. If you want to learn what error happened, truly learn, we destroy the information that we actually want to protect. Okay, so what we do instead is we measure syndromes, right? So we already and by these syndromes kind of give kind of circumstantial information about what's going on in the system. In particular, we're measuring the stabilizers, the S1 and the S2. Okay, and the nice thing is that we learned in the previous session, we are allowed to measure the stabilizers because they commute with the logical state, with the logical information, with logical operations. Even if you measure the stabilizers, the logical information is protected. It's not affected. Okay, so we can now measure the stabilizers S1 and S2, and we can look at the outcomes. Okay, if you measure now S1, this is just checking the parity in the first and second qubit. And you can see the parity of the first and second qubit is different, right? Because you have 1, 0. So therefore, the syndrome is flipped corresponding to what it's usually supposed to be. Because if there's no error, both syndromes should be 0. Like we should always get, so what we actually get is, if you measure the parity, we would get a measure +1 outcome, which we write in the syndrome vector as a 0. So this is a bit confusing, this part, sorry. But basically what it means, if the syndrome has its usual value that it's supposed to have, basically in this case, the syndrome outcome should be a +1, then we write a 0 in our syndrome vector. And if the syndrome has flipped to what it's supposed to be, then we write a 1. Okay, but this would correspond to measuring a -1. Okay, but this is just notation. Okay, so 1 means syndrome has flipped, and the first syndrome obviously has flipped because we have 1, 0, whereas the second syndrome, which measures the parity of the last 2 qubits, the parity of the last 2 qubits is just 0, 0. There's no parity, so therefore we write a 0. Sorry. So we have the syndrome vector 1, 0. Okay, which means basically first stabilizer has flipped, whereas the second stabilizer is unchanged. Okay, so once you basically see that the syndrome vector is not a simple 0, 0, it means something is wrong, some error has happened, right? Because if there's no error, then we would expect 0, 0. But since an error has happened, the syndromes have changed, therefore we know something bad has happened. Our code has been affected by something bad. Okay, so we now use our syndrome information to figure out what actually is going on. Okay, so for this, we now take the, so this is now what we call decoding. We're trying to find what error, the error vector, the error that's happened, by looking at the syndrome information that we have. So as I mentioned before, the syndrome information is only circumstantial information, and this becomes obvious now very immediately. Oh, sorry, there's a typo here. This one is not supposed to be here. Okay, sorry. Okay, so if you now look at the syndrome information is not unique, which is immediately obvious because we only have 2 stabilizers, but we have 3 possible errors, right? So therefore, it's not possible to uniquely figure out what's actually going wrong. And for example, in our case, where we have the syndrome vector 1, 0, you can really see this because there's 2 possible errors that match the syndrome information. Of course, what matches is the 1, 0, 0, the error that actually happened, X error, the first qubit. But you can also see that if you have an error 0, 1, 1, which is basically X flip on the second and third qubit, that produces also the same syndrome, right? Because if you do a parity check, you see the first 2 qubits have different parity, the second 2 qubits have the same parity. So basically you have now 2 possible choices, right? You could either have this one or this one. And just by looking at the syndrome, each of them is possible, right? Did they both match the syndrome? So meaning we don't really know how to fix this, right? Because if you just give the syndrome, and this is the only thing we have, we don't know, right? Do we have this error or do we have this error, right? So what do we do? And yeah, we have to make a choice. And we have to make the best possible choice that they can do. And the best possible choice is simply picking the error with the highest probability. Okay. Now we have to make an assumption. We assume that the error in your system is kind of low, right? So we kind of assume that, let's say, an X error happens with some probability P, and let's say the probability P is smaller than 1/2. So it's relatively low. In this case, the most likely error is the error with the lowest weight, right? Because, yeah, we assume that usually very few errors should happen. So I mean, the most likely error is the error with the lowest weight, so the error 1, 0, 0. Okay, perfect. So we can guess what is the error that's likely has happened. Now we make our guess. Okay, so as again, we have the X flip on the first qubit. So let's say somehow we are good and our decoder worked correctly. Then we apply a correction operator. And for this, we apply now the inverse error. So meaning we take the error that we predicted from our decoding and apply its inverse, which in this case is simply applying the same error again. So we had initially an X error, so meaning on the first qubit. So now we apply as correction operator an X operation on the first qubit. And these two will cancel because X times X, they're Pauli's, they just give identity. And we're back at our zero logicers, which is exactly what we initially started out with. So meaning now, although there was an error, we fixed it and we return to our original state. And you can basically show that this is independent of what we choose initially. So whether we have a zero logical or a one logical or any other linear combination, this will work the same way. So we can fix it. Perfect. So we're back where we want to be. So that's happy. Well, let's say we somehow made a mistake, right? So let's say we did our decoding and we made the wrong guess. We guessed the wrong error that matched the syndrome, the 011 error. So now we apply the correction operation, and the correction operation for this error would be to apply an X flip on the second and the third qubit. Okay, but this is bad because what actually happened is an X flip on the first qubit, right? So the resulting operation that we now do from the error plus decoding is applying an X string. So meaning we're flipping our zero logical into one logical. So now basically our quantum logic information has flipped from 0 to 1. So meaning we have now the wrong state. And this is bad because first of all, we didn't preserve the information correctly. And also we have no way of fixing this because the one logic sits within the code space. So we have no way of actually determining that we actually made a mistake. So after this, basically our information is ruined and we have no way of fixing this. So this is bad. So we also need to try to decode correctly because if you make a mistake, it may ruin our information. Okay, so what does this mean? That means whenever we do decoding, there's an error, a chance we make an error. There's a chance we make a mistake. But still, the only thing is this bad, like since we make mistakes, is quantum error correction kind of useless? It's not, because we can just think about it. Without error correction, let's say we have errors with probability P, right? An X error will appear with probability P. And we know that, let's say, if the error is, let's say, 100, so let's say one error appeared, then our decoding will work correctly, right? Using our decoding, we can just fix this error. But let's say we have now an error which looks like this, 011. This error appears with probability P squared, right? Because we have two flips. So therefore, the probability that this error appears is P squared. Now, if we now apply our most likely decoder, we try to fix it using this error vector here. We make a mistake, right? Because as we showed before, and we pick the most likely error, and this will then basically induce a logical error. Yes, because we assume the correction will be the most likely operation, which is the one with the one error, because that's probability P. Okay, so that means with decoding, we make a mistake with probability P squared. Okay, but that's fine because it turns out we can correct any error that appears with probability P. So basically, we have now an effective error suppression. Although we are not perfect, we still are able to correct errors that appear only one time. So basically, without code, we would have an error probability of P, like the probability that our information is destroyed is probability P. But with error correction, we fix all errors with that appear probability P, and only if errors that are on the order of P squared with lower probability will affect us. So the bottom point is we gain something, right? We basically reduced errors that we probability of an error from P to P squared. Okay, so my main point is that although decoding is not perfect, right, because it doesn't give us unique way of figuring out what is the best way to correct something, it still gives us some reduction in error. And as we increase the course distance, we'll get better and better. Okay, so this was the a very kind of simple example on how decoding works. I hope this was more or less clear, because now everything gets a bit more formal. But this is the main part. If you understand this, you know pretty much what's decoding all about. But it seems to be clear since you see no questions. Great. So now let's become a bit more formal. I will now explain basically how to actually decode on a formal level. I will explain for CSS codes for simplicity, but everything also works for any other type of code than just using CSS codes, because this is what you usually encounter. Okay, we already learned about CSS codes in previous sessions. Let's assume we have an nkd CSS code with n qubits, k logicals, and distance. We can then write out its parity check matrix, H, which is basically this kind of matrix that describes the stabilizer measurements. And for CSS codes, you can write them in this way because Z measurements and X measurements are completely separate. And for convenience, we can now basically just look at the Z syndrome measurements. So basically, we concentrate on this subsection. And these are Z measurements which detect X-type errors. And vice versa, the HX detects Z errors. But it's unlogically, so we can just figure out how HZ works, and then the rest follows immediately. Okay, so the parity checkment looks like this. It has the columns describe the syndrome measurements, and we have M of those. And each syndrome measurement is a stabilizer of the code, and it's written just this. It's just a tensor product of Z operations. And HZ is a binary matrix, so the entries are 0 and 1. 0 means that particular stabilizer doesn't measure the qubit. 1 means the stabilizer measures that particular qubit. Okay, and we have the number of columns is n qubits, and each basically indicates whether or not the stabilizer measures that particular qubits, because an error can happen there. And generically, the number of rows is simply the number of possible errors. So in case of Z errors, there's n possible Z errors, single qubit Z errors. Okay, and this basically conveniently summarizes our code. So by just looking at this kind of construction, we immediately know what is our code. So it fully characterizes a particular quantum error correction code. Good. Now, how do we do decoding? So let's assume some X error has happened. Then we write this in some kind of error vector E. So the error vector E is a vector of length n, where the different entries correspond to whether or not errors happen. If errors happen on a particular qubit, you get a 1, else a 0. You've seen this earlier for repetition code. This is just the same thing now in general. Now, if we do our stabilizer measurements, the stabilizer measurements basically react to the error. They make like parity checks between different errors. And physically, these correspond to some kind of measurement operation, which we'll talk about later on. But for convenience here, what happens is you can write them simply as multiplication of the parity check matrix times the error vector, modulo 2, because it's all binary, because we're just doing checks, parity checks. And the resulting vector is the syndrome vector, which is a vector of length m, basically indicating whether or not the syndrome has flipped. Basically, whether the stabilizer is what it's supposed to be, or it has flipped a value because some error has happened. Okay, now we have to do decoding. And what we usually do is something called maximum likelihood decoding. Basically, finding the most likely error, E, given the syndrome. Namely, we're trying to find an error that matches the syndrome condition, basically parity check matrix times the error. And we're trying to find the error that is the most likely, given some prior information. And as we already learned earlier for the repetition code, the first condition or the syndrome does not uniquely specify the error. In fact, there's usually exponentially many different possibilities. So we need to do some optimization and basically check over all these possible errors that match the syndrome, which is the actual one with the lowest probability. This is the best we can do. Okay, and optimally, how we solve this is basically by running some optimization problem. To specify what it means to be most likely, what we do is we basically need to know, given the jth qubit, what is the probability pj of an X error appearing. So we need this information beforehand, which you can basically achieve by using, let's say, tomography or some kind of benchmarking. You need to basically characterize your system and figure out what is the probability of errors occurring for every possible error. So you need to know this information beforehand. So you need to extract this. You need to learn about this somehow. Then we can write down the total probability of a particular error configuration E. So for every error configuration E of all the errors, we can write down its probability. And the probability is simply basically the product of all the errors, and we basically multiply either pj, if an error has occurred for the particular qubit j, or 1 minus pj, basically the probability of no error occurring when no error has occurred. And we can rewrite this in this nicer form here, where this is some kind of constant, and then basically this is something that depends on the error. Okay, and then we can write this whole thing as an optimization problem. In fact, this is a linear program. Basically, we maximize PE conditioned on the syndrome condition. And for convenience, we put logarithms in front of the probability of the total probability, because this makes everything much nicer to write down. Because then the maximization of all possible errors is simply some constant minus some summation over some weights for each possible error. So this is just some binary numbers that we have to optimize over. And the weights is some kind of number we can calculate. Okay, and this can be by doing some basic calculations. You can show this is a linear program, and people have shown this is in fact an NP-hard problem. So in the worst case, solving this problem is intractable. It will take exponential time. And this actually has some very funny implications. That means whenever we want to do decoding on a quantum computer, we need to run a classic optimization problem, right? And this classic optimization problem, we need to solve correctly, right? Because if you make errors, then you're in trouble. So meaning we need to run an optimization problem on a classic computer, and this classic computer needs to have error correction inside, right? Because if we have a classic computer without error correction, then probably it will not solve this optimization problem correctly. So, and you can show basically using Clifford operations that one can easily run transversely, this optimization problem cannot be solved. So in other words, in order to decoding, we necessarily need error correction. So quantum computers always need classic computers together. Like you cannot have an error corrected quantum computer without a good classic computer. So this is kind of I think the bit irony, like in quantum error correction. To run a quantum computer, there always needs to be some kind of classic computer that works for us. Okay. And yes, so this was the main formal definition of how people do decoding. Are there any questions? Because then I will get more specialized topics. But if you understood what happened so far, then you're already good. Like this is the key point of what happens in decoding. Okay, no questions. Okay, so in my next slide, I will now contradict myself. And what I told you so far is actually not the full story. Because it turns out maximum likelihood decoding, what I just explained so far now, is not the best way to do decoding. Okay, so maximum likelihood decoding that I explained to you earlier is actually the way how you would decode a classical error correction code. So if you try to protect a classical system from errors, let's say if you communicate over internet or you store data on your hard drive, then always there is some error correction code there. And there's some classical computer that does the decoding to fix the errors. So this is how you do decoding on a classic computer as well. But quantum error correction is different than classic error correction. And similarly, also the optimal decoding is different than you would do in a classical system. And what I just told you right now is not the best way to decode a quantum error correction system. The reason is that quantum error correction would have some feature called degeneracy, which you don't find in classical system. And degeneracy means that different errors can have the same effect on the code words. And you know already, I think you already learned why this is the case. In particular, stabilizers leave code states invariant, right? And we can see this when this happens. Let's say we have a surface code, and let's say an error has happened, which we indicate as a red thing here, right? As a red dot. So there's an error happened here. Let's say an X error here. Okay, so this is a single qubit error, and if you do a syndrome measurement, this will be detected. Now we could, let's now think of a different error, where basically we have the same error again, plus we have an error on the plaquette. And sorry, these will not be detected by stabilizers because they occur into stabilizer operations. So therefore we cannot, because these errors are occurring to some stabilizers, they will not show up anywhere, right? Because that particular error is just a stabilizer. So meaning we can always basically take an error and modify it with stabilizer. It will not change the code set at all because it's just this particular error that we added onto is just a stabilizer. It is not detected by anything because it commutes with all the stabilizers as well. So my point is, each error has like many possible alternative errors that behave exactly the same way because they're just stabilizer modified errors, and we can't really distinguish them from the original error. So now, if you want to do maximum likelihood decoding properly, basically finding the most likely error, it's not enough to just basically take the error of one error configuration. You also have to take compute the probabilities for all possible logical equivalent errors, right, that have the same effect on the code. So basically, if you want to figure out what error is the most likely actually logical error, that's the only thing that's kind of invariant. You have to basically start summing over all equivalent physical errors, basically this error plus all its stabilizer equivalent forms, like where you add different stabilizers onto it. So I mean, the actual decoding problem involves summing over exponentially many different possible errors that all behave the same way. Whereas maximum likelihood decoding, all these different errors, which are stabilizer invariant, would be considered as the same error. As different errors. So they would consider them individually, but actually you're not supposed to consider them individually. You actually need to sum them together because they all have the same effect on the code. So this is called degenerate maximum likelihood. And this is the actual way, or the optimal way, to do decoding in a quantum computer. In practice, people have shown this is a sharp P complete problem, meaning it belongs to even harder class than MP. MP is already hard, sharp P probably is believed to be even harder than this. And maximum likelihood is, degenerate maximum likelihood is there's no really good decoders for it. I mean, there are decoders, but they're all very, very slow. And it's a very complicated problem. So what people in practice normally do so far is simply do maximum likelihood decoding, basically ignore this degeneracy problem, just do it. And it turns out in most cases, or cases that of practical relevance, it seems to work reasonably well. And maximum likelihood decoding seems to be good enough, and the degenerate part can be in practice ignored. And I mean, it gives better results. We show that degenerate coding gives better performance, but in practice, maximum likelihood seems sufficient for quantum computers to run, which is good because it makes things easier for us. Okay. Good. So far, I talked about how to decode errors that happen in your system. But this is not enough because you have to basically, if you actually want to run a quantum system or any complex system, in fact, as we learned from Shannon, you have to assume that everything is error prone, right? So far, we assumed only the qubits are prone to errors, right? We have our physical qubits where we store our logical information, and every physical qubit is subject to some error, so right, that affects them. But we have to make the assumption, but this is a very simplified assumption because, as I said, everything can have an error. In particular, the stabilizer measurements we do, right? We measure all the stabilizer, which is an operation we have to do. And again, this operation can be error prone. So meaning everything has an error, right? And we have to include this if you want to actually treat a realistic system that we actually run, let's say, on an experiment somewhere. Okay, so basically this assumption that the syndrome measurements, measuring the stabilizer, is noise-free is a simplifying assumption, which is not true in practice. In practice, we have to actually assume they're noisy. And for this, people proposed a phenomenological noise model, where basically we assume the syndromes itself are noisy. Meaning we make this assumption, which as we'll see in a minute is simplified again, that whenever we measure, let's say, a stabilizer, measure as before, let's say we measure our parity checks, that they can be flipped. So meaning, let's say we want to measure this stabilizer here, there is a chance basically that due to some noise or whatever, what happened, this measurement is flipped to what it's actually supposed to be. Let's say it flips from 0 to 1. And we assume this happens with some probability due to faulty measurements or some other thing happening. Now, this is a problem because if we, let's say, do a round of error correction, we measure all the stabilizers, we cannot distinguish errors in our data qubits, basically that one hold the physical information, from the error that happened in the syndrome, right? Basic example. Let's say we measure this syndrome here, right? 1, 0, from our early example from the repetition code. Of course, you could have, as we assumed earlier, you could have an error, let's say, where the first qubit is affected by noise. First data qubit is affected by noise. But we could also have a measurement error in the first stabilizer, right? Maybe the stabilizer just flipped for some reason. And there's no way to distinguish those two, right? Because yeah, either of those could happen, right? Okay, so meaning if you just do one round of error correction, we just do a single measurement of the syndrome measurements, we cannot really figure out what's going on. Okay, so what we actually need to do as a solution is we actually need to repeat the syndrome measurements d times, then only decode. So meaning we do the syndrome measurements, repeat them d times. So we measure, 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 and only after we've done the d measurements, we start to decode. Okay, so after this, you can now basically build a decoding graph that basically captures the parity check matrix, right? So you can again build a parity check matrix. Now it's a bigger parity check because now you also have to include all the d repetitions and you have to measurement. But again, this will be some kind of parity check matrix. And then you can decode. And it turns out measurement errors have different signatures than qubit errors. And you can easily see this because, I mean, yeah, once you have more qubits, you'll see they have a different structure. That's very easy to see. Let's say in a case of, let's say a data qubit error happened, right? Let's say the first qubit is affected by an error. Then the first syndrome will be flipped, first time you measure. Then let's say you measure the syndrome again. Then again, the syndrome will be flipped, right? Because the error is still there. However, let's say if you have a syndrome measurement error, then let's say this will happen with hyperbole only one time. And the next time I measure the syndrome, there's no error, right? Because the flipping is probabilistic with low probability. So meaning what I want to say is that basically data qubits and syndrome measurement, they have different characteristics and therefore can be distinguished. And you can distinguish them when you do repeated measurement d times. Okay, so that means whenever we do quantum error correction, we have to repeat stuff a lot of times. So this is a space-time overhead you have to always conclude in. Okay, and again, this was not the full story because I simplified again things. Because so far the noise model for the syndrome measurement is very, very simplified. Basically, what I said is just error model where I assume that the measurement error just flips from 0 to 1 or vice versa, right? But this is actually not what will happen because if we actually do quantum error correction, what we actually do is we measure the syndrome, and this is a physical operation. So every time you have to measure the syndrome, you have to run a quantum circuit with gates. For example, if you want to measure the Z syndrome in the surface code, then the corresponding circuit for measuring one syndrome of the d squared minus 1 that we actually perform look like this. We have our data qubits. Let's see the surface code. We know the X with 4 qubits, right? It's a weight 4 check. So we have basically, let's say, a plaquette consisting of 4 qubits. This is where we hold our physical information. In addition, we now prepare an ancilla, which we call the measure qubit, and that ancilla sits in the middle of the plaquette, right? Let's say we have one plaquette here, which is like this, right? Then the measurement qubit will sit in the middle of it. And this will then, and this measurement qubit now interacts with the surrounding data qubits via CNOT. And basically what the CNOT does, if the CNOT is basically implementing now we apply the CNOTs and then we measure. And you can easily show that this measurement operation corresponds to measuring the syndrome. It's basically doing a projective measurement onto the syndrome, onto the stabilizers, and then the measurement outcome that we measure here gives us the syndrome. Okay, and one can show this allows us, for example, to detect X errors, and there's a similar circuit also for detecting Z errors. Okay, and this model is the gold standard people nowadays use to do quantum error correction. And here basically you have to assume actual quantum grains and actual physical noise models that people know from is a realistic description of a quantum circuit. So people call this circuit level noise. And what kind of noise this usually includes? A typical noise model would include, let's say, first of all, the measurement qubit has to be prepared. So there's a state preparation error. So every time we do a syndrome measurement, or measure stabilizers, we have to prepare this measurement syndrome. This oscillar. And there can error happen, right? Let's say the initial state is 0, but let's say there's error happening and actually we prepare, let's say, the wrong state. Let's say the state 1. So this error can happen. Then we apply our CNOTs, right? The CNOT is a 2-qubit operation, and this will induce some 2-qubit error channel. For example, a 2-qubit depolarizing channel, which has 15, and if you write it out in the cross map, you find there's 15 possible errors that can happen, like identity, XX, XY, XZ, ZX, ZX, and so forth, like 15 of those, so you can count them out. So there's a lot of possible errors, but every CNOT, there's 15 possible errors that can happen. And now there's a lot of CNOTs, as you can see, right? We're applying 4 pair stabilizer measurement, and we have d square stabilizers, d square minus 1 stabilizers. So you can count there's a ridiculous number of errors that happen every time, that can happen every time. Additionally, we also have idle noises. Just, let's say, whenever our data qubit is, let's say, doing nothing, an error can happen, right? Just by, let's say, photon loss or decoherence or whatever, right? T1, T2 time, whatever. So just doing nothing also induces errors. And we can also have measurement errors, right? Because whenever you measure something, the measurement apparatus itself is noisy, right? Because when you do the measurement procedure, something bad can happen. Or you can make a mistake in a readout, right? So my point is, many things can go wrong, and you have to keep track of all of them. But you can simulate this. It's all efficient, assuming for a large class, basically the usual class of noise that we expect. That's the wrong slide. There's an efficient way to simulate these noise models. And we will do this in a minute. How much time do we have left? 15 minutes or so, I guess. Yeah.
15 minutes, yeah.
10 minutes.
15 minutes, yeah.
15 minutes.
Okay. 1 5, yeah.
Yeah, got it. Okay, good. Yes, so this is my last slide before we go into the coding tutorial. I just want to basically motivate why these questions are important. And for this, I just want to refer to one of our recent papers we did together with Kishore and some students from NUS, which is a very nice work. You should check it out. But I just want to explain why this is important. And I want to show this basically by using recent research. And we asked a very basic question, basically. Let's say we have a particular code, NKD. Whenever we compute the, let's say, the code distance of a code, we work in the simplified error model, right? We basically assume that this is normally used as what people call the code capacity model. They basically assume the measurements are noise-free. And basically there's only errors in the data. So it's a very simplified model where people compute the distance. But is this actually the best way to do it? Like, you can ask the question now, if you actually run it, everything has to implement in gates, right? So we go away from the simplified error model and we actually have to run everything in circuit. And you can ask the question now, after doing all this, is the distance still the same, right? Or is the distance different than before? Right? Because, I mean, as I said before, when people compute the code distance, they use a very simplified noise model. But if you use an actual circuit, does it still even make sense? Is the distance the same or not? And this is actually a highly non-trivial problem, which is not solved to my knowledge. I mean, you can just check, but it's not really clear how to answer this question. But we can make case studies. So we made a case study for a particular code, for a particular ADPC code, but it doesn't matter. It's some kind of code, a 34.5 code. So it has distance 5. This is important. And then you can try different ways to read out the syndromes, right? So basically, there's a code. It looks like this here. And there's a bunch of syndrome measurements you have to perform. There's no stabilizers and syndrome measurements, and you do them, all of them. And you can now look at them and ask, how to actually read them out? And it turns out actually how to read out syndrome measurement stabilizers is not unique. There's pretty much an expansion number of choices how to do it. You can do a naive way of reading out. So we try different ways. So you can, for example, just take the synonym measurements, right, which are basically a bunch of synods and measurements. And you could just starting them reading out sequentially, right? So basically, first you measure the Z syndromes, and after you finish measuring your Z syndromes, you start measuring the X syndromes, and then you repeat. Okay, you can do this. This creates a kind of deep circuit. For example, in this case, is the def10 circuit. But if you then start computing the distance of the code, including circuit level noise, you find a distance of 4 circuit level. So meaning it's different, right? Because this is actually a code, distance 5 code. But after including all proper, more realistic noise model, like including all the circuit level noise, you find distance goes down to 4, which is bad because that means the code is actually worse than we hoped for. Okay, now you can think, okay, maybe let's find a better way to read out. So there's been some proposal how to make the readout better by basically intertwining X and Z measurement. You don't do it sequentially, but you start reading out, applying the CNOTs for the XZ readout and the readout for the XNOT at different times. So you can somehow, if you think about it, you can interchange them and do it kind of one after the other. Sorry, at the same time. And this gives you a shorter circuit. But if you, let's say, do it in this particular configuration, which was proposed in some earlier work by Bravi et al. From IBM, you find again the distance is only, the circuit level distance is only 4, below what it's supposed to be. And okay, this is disheartening, but then okay, maybe we can do better. So we start rearranging. We start just playing around and trying to rearranging the CNOTs. And after a bit of try and error, basically we found this configuration here, which is different than this one. You may look closely, but you can see you now apply gates at different times. And if you do it this way, it turns out you get now a circuit level distance of 5, the one that we expect. And you can also do then some further studies and basically show that the logical error against the physical error, you find that depending on how you read out the errors, you get different error levels, right? You can see, let's say the blue curve, which is the sequential readout, has a higher logical error rate, whereas the green one has a much lower error rate and also a better scaling in terms of error, right? Because you can see logical error decreases much faster with physical error rate and has a better threshold, absolute threshold. So my point is that I want to make is how to actually do the syndrome measurement is very important, and you have to actually think about it hard once you actually consider realistic noise, how you would see an experiment. And how to do this is totally not obvious. Like there's a lot of degrees of freedom, and it's not clear how to do it in a good way or the best way. But it makes all the difference if you actually want to do physical experiments and actually run a quantum error code in practice. So this is some question I posed to you, or it's an open resource question pretty much. Okay, so I hope this motivates some why this is important. And now we get to the last part, which is the coding tutorial. This will be very short. We're going to use the standard tool that pretty much everyone uses nowadays, which is called STIM, which was written by Google, mainly by Craig Gidney from Google. And this is a nice tool that efficiently simulates quantum error correction codes, which are based on stabilizers, so Clifford operations. And maybe I don't have time to like this time, but basically this is also necessary when you actually want to do run an experiment, a quantum experiment on a quantum computer physically. You actually have to run STIM in parallel, or you have to run STIM before at least to characterize the noise there and build all this detection code and so forth and build a parity check matrix. So my point is this is a very important tool both for simulation as well as also for running experiments. Can't live without it. Nice thing, it's a Python package, so it's very easy to run, and it pretty much handles everything. So once you have it, you're pretty much done. You can just run it. And as I said before, it's the detector model, the tunnel graph that you actually need for experiments. Okay, let's do it in practice. For this, I need to switch my computer because I can run the code only on my other computer. So give me a second while I switch over. And I have to stop here. Right. Okay. Yes, you can see me. Perfect. Can you see my? Wait, I didn't share. Sharing. Oops. No, sorry. Give me a second. Sorry. I think you're supposed to see now my screen. Perfect. So I'm just gonna very shortly go through the getting started So this is a Python, the environment to run stim, and what I'm showing you now is just a notebook, pretty much a notebook. I just modified a bit, but the original notebook is found on the stim website. So if you want to use stim, you first have to run basically this basic code here. You just basically import stim and also import the decoder. You can do this here. It should run already. Okay, perfect. So once you imported everything, okay, it's done. We actually can start decoding. So first, what you have to do is you have to first generate your circuit, right? So the conversion code, once you have a conversion code, you can basically turn this into a circuit. And stim already has some circuit pre-programmed, but you can also just make your own circuits if you want. Let's run this code here. Basically, what this thing does, it basically, in this case, loads a repetition code. And you can see the distance 9 repetition code, and basically repeat the measurements 25 times. And you can do some deposition error and also some bit flip error. So you can also change what errors happen in the system. And basically, the stim circuit is basically just a set of operations, right? Because in the end, what the conversion does is just a set of operations where you basically measure your stabilizers. And the stim circuit basically is then written out in terms of some gates, and there's some ESD products, so there's some errors happening, and there's CX, which is some CNOT gate, and so forth. And there's also then measurements and detectors, which basically just evaluate the measurements. And you can also, it has some kind of program feature where you can repeat operations, like if you want to do measurements many times, it does that for you. But in the end, it will just write out everything in terms of human readable format that characterizes your conversion codes. This represents, let's say, a repetition code. And also has a nice feature of drawing out the actual code that's happening. So what actually the physical operation that you need to run your code is then just written out in terms of gate operations and measurement operations in this nice form here. Okay, so once you have that, you have now your code and the gates, and it calculates the error. And as a next step, it will write down the detector model. So, sorry, first it will basically sample errors. So basically, given this error model, it will then basically induce errors and basically sample different error configuration. And you can have this program now sample different possible errors that happen in the system. So you just sample errors according to the corresponding error probabilities. And it will also write down the error detector model. So basically, this detector model, you can think of this is pretty much what we earlier called the parity check matrix. It's effectively the same thing. It's simply saying basically for each error, it will say which detector has been triggered. So basically, it connects errors with detectors. And you can basically, and you can show this is equivalent to some parity check matrix. So basically, it's a kind of a thing that writes down how each error affects each particular detector and flips which physical operations and so forth. And using this, this is the thing you need for decoding. Let's say if you want to run a quantum experiment or a numerical experiment, you need this thing to help you with the decoding, because that is the information you need for the maximum likelihood of decoding. Okay, as the final step, we can now simulate errors and then have them decoded. And in this case, we use something called the so basically this program now, this line of code basically generates errors and then runs the decoder. In this case, is the matching decoder, which we'll talk about in the next session. It's basically some way of some program that basically decodes things. And it's a decoder that tries to find the most likely error, but it's doing some approximations. And after running it, basically it generated 100,000 shots, and the decoding was wrong 4 times, and else it was correct. So it worked quite nicely. Okay, and as a final step, you can also play around with the error rate. So if you want to increase the error rate, let's say, we can error rate so far was 0.3, we can increase it to 0.1. And as you will see, this will, for example, then increase the number of logic errors where the decoder make a mistake. You can see now we have 1,342 wrong predictions, right? So the decoder was wrong now far more often because the error was more strong. So decoding became more difficult. And the nice thing is stim is super fast, so you can run many things, many 100,000 shops in a matter of seconds. And finally, we can do some kind of pickup plot. We now try different noise levels. And we try also different code distances, and we sample many shots, and we plot everything together. And so basically now plot is x-axis the physical error rate that actually happened, and then the y-axis is the logical error rate. And you can see we have now different code distances. And you can see the lower the code distance, the lower the error rate. Let's say distance 7 code, you can see the error decrease much faster than, let's say, for distance 3 or distance 5. And distance 1 corresponds to just having a physical qubit without protection. And you can see that if the physical error is quite high, then having no error correction code can be better, right? Because then you see the error rate of the correction code. Error correction code is higher than the blue line without error correction. But if you decrease physical error, at some point you find the pseudo threshold, where basically decoding, like using a quantum correction code, is better than having no quantum correction codes. And at this point, you gain a lot. So yes. Okay, so this is very short coding tutorial. The heavy lifting is thankfully done by the actual code, by the package. So everything is relatively easy and straightforward to do. If you want to run your own experiments, it's barely a matter of minutes to program it. Okay, with this is then already the end of the first part, and then we will talk about the second part next week, same time.
Okay, thank you, Tobias.
Yeah, thank you.
Any question here? Okay, actually, I have one stupid question here. So
yes.
like you mentioned that we can end up with some like wrong error syndrome when we analyze the syndrome, right? Like so we can apply the wrong recovery process.
Yes. Mm-hmm.
So I have a question, like, do we always end up with the logical error, like when we perform a wrong recovery after decoding? Is it always the case? Like, is there any case that we can like by accident correct the errors or something?
Yeah, of course. I mean, there's always a chance that basically that although the decoding went wrongly, that you make the correct correction operation, right? Because you know, like convection was a degenerate, right? So
yeah.
So there's a chance basically you pick the wrong error, but since it's the same, the correct error up to some stabilizer, then it's fine, right?
Okay.
So there's many instances basically where you basically pick the wrong error, but actually you're still good. So there's always some leeway. So usually, yeah, it's fine. But yeah, I mean, you can also just by chance make the correct choice.
Okay, thank you. Any other questions here?
Shubham, I think your hand was raised. Maybe you had a question.
Oh, sorry, that was an accident.
Ah, okay.
Okay, so if there's no questions, we just stop here. Thank you, Tobias, again. Like, it's a fantastic tutorial today. Yeah. Okay, thank you, everyone. See you next week.
Thank you.
Thank you.
Yeah.